and welcome to this edition of workshop number 2, mid-surface extraction example. I believe to understand the importance of this, we need to first discuss what is a mid-surface. A mid-surface is a thinner representation of a model. So what does this do for us? It simplifies the analysis by making a 3D actually a 2D analysis, and splitting up, if you may, the model into surfaces. So we're going to start with the simple. We're going to go into new. We're going to create a database. We're going to call it mid-surface database, mid-surface 2 actually, because we've done a few other examples about this. Go right in and just save it there. So we just make sure that the code is Nastran again and the analysis is structural, and we just go tolerance is based on the model. We click OK. So something we have to keep in mind, our patron in this course is only a student edition, which doesn't allow us to create a mid-surface off of the software. So what we have to do, what we had to do, because we're prepared just to go into the analysis of this model, is create a model of the mid-surface in another software. So what we did was create the analysis in SolidWorks, and we're gonna actually, instead of importing the entire JBox, which is the name of the model, we're just gonna import the mid-surface file. And what we're gonna do is we're just gonna let our model have a sort of an isometric view so you can see what we're working with. At this point, our next step, if we had created the mid-surface here, would be to edit the gazettes in order to make them triangular and not have an extension which is just vertical. But since we did the model on a much simpler software, that step is not necessary at this point. So what we have to do is associate the actual gazettes to our vertical components, and the gazettes are associated under geometry. So we click geometry and we go to associate point curve method. So what we're going to do is just curve, which is much easier. So we're going to go to each gazette and click our vertical components. And under the second curve, we're going to click on the face. We're going to hit apply. So what we have there is an association between these 2 points, and we're going to just uncheck auto execute just to make it much simpler, and you can start seeing the nodes being formed. So we're just gonna, I'm gonna skip ahead because I don't want to show this in the video. I don't want to show you me clicking and adding, so I'm just gonna do that after the break. Right after the association of the gazettes to the frames, a couple of steps were taken. First of all, we did a meshing, and I can't show you the process right now because it took quite a while to do. So what we're gonna do is just recreate the steps. We're gonna create a mesh, and this is the node number and the element number. It's a paver mesh, quad 4, and our value was actually set to 9 because of the element limit and the time it had to take. So that was the meshing made. After that, we go to our loads, and what we did, we created a total load, and we're going to see the input data, and the data was 100, a load of 100 on the Y axis. So we're going to actually change that because of the orientation of our model was changed. So the that was 100 on the load, so it went towards Y. So what we want to do is go towards the back holes, and we're going to do a load of negative 100 on the x-axis. Okay. We're going to apply. We're going to override that load. And as you can see, the orientation of our elements has changed. After the load was created, what we did was go right into our constraints. Which have to be set as a displacement nodal, and it's called fixed. You see our input data. We're not going to allow any translation or rotations, and the load constraints were set on the bottom holes. So as we can see, there's going to be a load towards the back part of the box, and constraints, total constraints on the bottom portion of it. Next up, we need to create the material we're going to use for our analysis. So we're going to go right into isotropic material, and as you can see, I already updated the database to call it aluminum, and I'm going to show you the properties of aluminum. So we're going to go to aluminum, and we can see that it's 10 times 10 to the 6th as the elastic modulus, and a Poisson ratio of 0.3. Going to click OK, and we're just going to leave it be for now. Next up, we have to add the material to the element, so we're going to go to properties, create. What we're going to do is go to properties, create a 2D shell. As we can see here, we already have it created. It's called 2D shell, and as you can see, the material we updated, we gave it aluminum and a thickness of 1/8 of an inch, or a patron unit if you may. And after this, we're going to go and check that it's homogeneous and standard formulation. Our input properties are set, so we're going to go right into the selection of the application region, and as you can see, I selected every surface on the element. Our following step is just to run a simple analysis. We're going to go into the analysis, analyze the entire model on a full run, and we're going to check our output right now. So we want a linear static solution to its parameters. In the output format, we want, of course, XTB and print. Click OK, and we click on the subcases, and just make sure that the default load case is selected. Just click apply and cancel, and the analysis is ready to be made. So what we're going to do is we're going to click apply, override it. The analysis is being run as we speak by the black box known as Nestrin. And now we want to access the results, so we go to results. In analysis, we go to access results, and you attach the XTB file, and we're going to select it. And now we're going to click apply. So the file has been attached, as we can see here. So now it's time to access our results. So we're going to go into results, create deformation, and we're going to go right ahead and jump straight into these results. under result cases, we're going to select default A1 static subcase, and we're going to select displacement translational or resultant, and we're going to hit apply. So this is the translation that's been made. The force pushing that way is going to create this displacement in pattern units. Now we're going to go to display attributes, and we're going to hide the undeformed and the title. After this, we're going to hit apply, and we're going to go to our After we see these results, we're going to go into our display attributes window, which is under deformation, and we're going to hide the undeformed and the title. We're going to hit apply. So we're going to go into our home, plot erase, and we're going to erase the geometry so we can just see the deformities shown by the force being applied through the constraints. We're going to go to our results once again, and we're going to go into the fringe marker, and we're going to check the stress tensor, and we want to check out the von Mises and quantities. And we're going to hit apply. We're going to see how, of course, the greatest stress is where the force is applied, and it's creating a lot of stress there, as you can see by the numbers. This is what we want to see. We want to see the coloring and how the stresses are increased in the areas of greater stress concentration due to the geometric factors that are in place at our von Mises points. In conclusion, we would like to say that this workshop was completed successfully, and we did not have too many problems solving this pickle that was posed upon us by the student edition. So thank you very much, and that's it for this section.